Welcome back to the deep dive. We're here again to cut through the noise and get you that actionable knowledge.
That's the plan.
And today we're tackling a filament that is, well, both a workhorse and sometimes a real source of frustration. PETG.
Ah, yes, PETG. It's got that dual personality, doesn't it?
It really does. It offers fantastic strength, great resilience, chemical resistance, all the good stuff. But it often drives users crazy with things like, adhesion chaos or just endless stringing.
That's a perfect way to put it, the filament with an attitude, if you're coming from something easy like PLA.
Which is so forgiving.
Exactly. PETG forces you to kind of slow down, pay real attention.
Yeah.
So our goal today is basically a clear, practical roadmap.
Right, how to actually tame this material.
Yeah. We need to look really closely at prep, the hardware side, and those slicer settings. Because, honestly, success with PETG, it all hinges on respecting its specific demands.
Okay, let's start there then. The non-negotiables. The machine itself. You can't just, load PETG onto any old printer and expect magic, right?
No, definitely not. You need heat. Lots of it, really.
Yeah.
First, the heated bed. Mandatory, no question. And you need it running consistently, somewhere between 70 and, say, 90 degrees Celsius.
And that heat's doing what exactly? Adhesion? Warping?
Both. It's essential for getting those layers to lock together properly, and it really helps minimize warping, which PETG can still do, especially on larger prints.
Okay, heated bed. Check. What else?
Second, you got to look at your hot end assembly. PETG prints hot. Generally, you're in the range of 230 to 255 degrees Celsius.
Okay, and 255, that number should probably set off a little warning bell for people with stock setup.
It absolutely should. That high temperature is right there at the limit, maybe even slightly beyond, where those common Teflon or PTFE tubes inside many standard hot ends start to degrade.
And that's bad news. Toxic fumes, right?
Toxic fumes, yeah. And it also just ruins print consistency. Yeah. So for reliable long-term PETG printing, an all-metal hot end is, well, highly recommended. It just removes that whole risk of PTFE breakdown, makes things safer and much more consistent.
Good advice. Okay, so hardware sorted. Now, before we even think about slicing, let's talk about what I think is probably the single biggest reason PETG prints fail, no matter the hardware.
Let me guess. Moisture.
The silent killer. Moisture, you got it.
Yeah, PETG is intensely hygroscopic. It just sucks moisture out of the air like crazy, faster than almost any other common filament.
So even if a spool feels dry, or it was sealed, it might not be.
Oh, definitely. Even if you've only had it unsealed for maybe a week in a normal room, you've likely absorbed enough moisture to really sabotage your prints.
And you can sometimes hear it, can't you? That dreaded crackling or sizzling from the nozzle?
Exactly. That's the water hitting the hot nozzle and instantly turning into steam, literally fighting its way out.
And those little steam explosions cause what?
Problems.
Big problems. They cause nasty surface blemishes, inconsistencies. They seriously weaken the final part because they mess up layer adhesion, making the print brittle. And of course, wet filament is probably the #1 cause of that awful spaghetti-like stringing. So the unavoidable solution is drying the filament properly.
Mandatory drying, absolutely.
Okay, but the parameters you mentioned earlier, 65 degrees Celsius for 6 to 8 hours, that's almost a full workday of just drying before I even start printing.
It really is.
Is it truly that critical, even if the spool felt okay?
Look, if you want high-quality, reliable, functional parts, yes, it's non-negotiable. 6 to 8 hours at 65°C really resets the material, gets that moisture out.
Okay, what tools do we need? Can I just stick it in the oven?
Well, specialized filament dryers are obviously ideal, but an affordable food dehydrator often works great. You just might need to remove some trays to make the spool fit.
And the oven. You mentioned caution.
Extreme caution. If you use a regular electric oven, you must ensure the temperature is accurate, steady, and low. Ovens can overshoot temps, which could damage the filament or even the spool itself. So proceed with great care if you go that route.
Safety first, always. And once we've done all that drying,
Right.
we have to keep it dry, right?
Correct. Once it's dry, straight into an airtight container or a good sealed bag, and throw in some fresh desiccant, like silica gel packets. Keep that moisture out.
So preparation really is everything here.
It truly is. Otherwise, all the slicer tweaking in the world is just like putting a Band-Aid on a fundamental problem. You've got to start with dry filament.
Okay, makes sense. Dry filament, check. Right hardware, check. Now let's get to that moment of truth. The first layer. This is where PETG throws another curveball. Because the issue often isn't that it won't stick.
It's that it sticks too darn well.
Exactly. Explain that paradox.
It's fascinating, really. PETG can actually form a chemical bond with certain surfaces, especially things like smooth PEI sheets, which are really common.
So, print directly onto smooth PEI and
You risk literally tearing a chunk of your bed surface right off when you try to remove the print after it cools. It bonds that strongly.
wow. Okay, you're saying this stuff can actually damage the printer. That sounds like an expensive mistake.
It can be a very frustrating and expensive lesson.
So what surfaces are safer? What avoids this, like, destructive bonding?
The ideal choice, generally, is a textured steel sheet, often powder-coated PEI. That rougher surface still gives you great adhesion while it's hot.
But the texture breaks up the bond.
Exactly. It seems to interrupt that super strong chemical bonding, so when it cools, the print usually pops right off, no damage. A satin steel sheet can also be a pretty good compromise.
Okay, but what if you have to use glass or smooth PEI? Then we need the separating layer, right?
Yes, the crucial separating layer. And remember, its main job isn't just to add stickiness, it's to act as a barrier.
A barrier against that destructive bonding.
Precisely, to prevent that chemical fusion.
Mm.
And it doesn't take much. A thin coat of a simple PVA glue stick like Core's is popular, works wonders.
Hairspray, too, I've heard.
Yep, something like 3D lac, applied lightly, creates a thin protective film. Even just wiping the bed with a standard window cleaner, the non-ammonia kind, can leave enough residue to act as that necessary barrier.
Interesting. Okay, barrier down. Now the final piece for the first layer, Z offset calibration. And this is totally counterintuitive if you're used to PLA.
It really is. With PLA, we want to deliberately squish that first layer down onto the bed, flatten it out a bit so it looks perfectly melded.
Right. Get that good smush.
PETG hates being squished like that. For PETG, you need to set a slightly higher Z offset. That means a slightly greater distance between the nozzle tip and the build plate.
Okay, walk us through the visual. Why does that PLA squish technique fail so badly here? What happens?
If the offset is too low, the plastic doesn't have enough space to extrude cleanly, so it starts to curl up around the nozzle, accumulate there.
And then it drags.
It drags and tears up the lines you've just put down. It's a mess.
Okay.
The visual goal for a perfect PETG first layer is for the lines to be laid down neatly, side by side, touching perfectly.
But not deformed.
Exactly. No signs of being squashed or pushed sideways, just nice, clean, roundish lines sitting next to each other.
So the rule is simple. If you squish PLA, you need to back that nozzle off a bit for PETG. No squish equals success.
That's the key takeaway for the first layer Z offset.
All right, let's move into the slicer settings then. We've got our first layer hopefully sticking nicely now. Let's talk heat again, but this time for the nozzle during the print and balancing strength versus surface quality.
Okay, so we already established that standard range, roughly 230 to 255 Celsius. Now, if your absolute top priority is maximum strength, maximum layer adhesion,
Like for a functional part?
exactly, then you'll want to creep towards the higher end of that range. Maybe 240, 245, even 250 Celsius.
But there's a trade-off.
Always a trade-off. Pushing the temperature higher usually makes stringing significantly worse. And it makes printing complex overhangs much trickier. They tend to droop more.
So start where?
Always start right in the middle of whatever range your specific filament manufacturer recommends. Then tune up or down based on your results and priorities.
And the bed temperature. Does that stay steady at 70-90 after the first layer? Or do we adjust?
Generally, you keep it stable in that 70-90 range. Though, as we hinted, many people find bumping it up maybe 5 or 10 degrees just for that first layer can help lock it down really well before dropping back to the main temperature for the rest of the print.
Got it. Now, print speed. This feels like another area where PETG demands patience.
Oh, it absolutely rewards patience. For proper thermal bonding between layers, you need to give it time. General print speeds should stay pretty conservative.
Like how slow?
Somewhere between 30 and 60 millimeters per second is a good starting point for most prints. And the first layer, always slow. Like 20 to 30 millimeters per second, period. No rushing that.
Okay, slow print speed. But then travel speed when the nozzle's moving but not printing, that's the opposite, right? Which feels confusing.
It does seem counterintuitive, but it's actually a key weapon against stringing. When the nozzle isn't extruding, you want it to move across open space as fast as possible, like lightning.
How fast are we talking?
Set your travel speed high, 120 millimeters per second, 150, even higher if your machine can handle it without violent shaking.
And the logic is?
Fast travel minimizes the amount of time that molten plastic has to just sit there and potentially dribble or ooze out of the nozzle while it's moving over gaps. Less time moving means less opportunity for strings to form.
Makes sense. Speed paradox noted. Slow print, fast travel. Now, the cooling fan. This feels like the ultimate compromise with P2G. How do we balance strength versus detail?
It really is a balancing act. If you want maximum mechanical strength, the best possible layer bonding,
Then you want minimal cooling.
ideally, yeah.
Hmm.
Turn the part cooling fan off completely or run it very, very low. Slow cooling allows the layers to fuse together really well thermally.
But what if my model has fine details? Or sharp corners? Or overhangs?
Then you have to compromise. You'll need some cooling to solidify the plastic quickly enough to hold those shapes. In that case, try setting the fan somewhere in the 20 to 50% power range. It's a trade-off between strength and detail fidelity.
And the rule for the very beginning of the print still applies.
Absolutely fundamental rule.
Yeah.
No fan for the first few layers.
How many layers usually?
Typically, the first 1 to 3 layers, print them with zero cooling fan. This prevents the initial layers from shrinking too quickly due to the airflow, which could cause them to lift off the warm bed or warp.
Okay, no fan early on. Got it. Finally, after drying the filament, the other major weapon against PETG stringing, retraction settings.
Yes, getting retraction tuned correctly is vital. The distance settings depend heavily on whether you have a direct drive or a Bowden extruder.
What are the typical ranges?
For direct drive, it's usually quite short, maybe 0.5 to 2 millimeters. For Bowden setups, because of the longer filament path, you need more, typically somewhere between 3 and 5 millimeters.
And the speed of that retraction?
Moderate speed works best, around 25 to 40 millimeters per second. Be a bit cautious here, though. If you set the retraction speed too high, the extruder gears can actually bite too hard and grind a chunk out of the filament.
Ah, the dreaded filament grinding. Avoid that.
Definitely avoid that. It leads to under-extrusion later.
Okay, and beyond distance and speed, any other slicer tricks for stringing? I always enable wipe.
Yes. The wipe function is extremely effective with PETG.
What does it actually do?
It tells the nozzle, right before it's about to travel across an open space, to quickly move back over the perimeter it just printed, by a tiny amount. It physically wipes off any small blob of molten plastic that might be dangling from the nozzle tip before it starts the travel move.
Clever. Like wiping its feet before crossing the carpet?
Exactly like that. Reduces strings significantly. Z-Hop can sometimes help too, but use it cautiously, as occasionally it can make stringing worse by giving the filament more time to ooze during the lift.
Okay, lots to consider in the slicer. Now let's assume we've successfully printed our part. It's off the bed. But printing is only half the battle, right? If you want a really professional finish, especially with PETG, you've got to embrace post-processing.
You really do. PETG doesn't hide layer lines very well.
So, initial cleanup, what's step one?
Standard stuff first. Carefully remove any support structures using maybe a scalpel, flush cutters, or tweezers. Then you'll likely have those superfine, wispy stringing hairs left over.
The ones that seem impossible to just pull off.
Yeah. The best way to deal with those is a quick, swift pass with a heat gun on a low setting, or even just a quick flick of a lighter flame across the surface.
Be careful not to melt the model itself, though.
Absolutely. Keyword is swift. You're just trying to zap the fine hairs, not deform the actual part surface.
Okay, string's gone. Now sanding. Here's where PETG's toughness actually becomes a bit of an advantage over, say, PLA.
It is kind of its saving grace for finishing. PETG is tougher and has a slightly higher melting point than PLA. This means it resists melting or getting gummy and forming lint quite as easily when you sand it.
So you can be a bit more aggressive, maybe even use power tools.
Carefully, yes. You can often use electric sanders, cautiously, on low speed settings. Start with coarser grits, maybe P120 to P240 to knock down the main layer lines. Then gradually work your way up through finer grits, P400, T800, P1200, even higher. Always use light pressure and keep moving. Circular motions are good.
And I'm a huge advocate for wet sanding here.
Oh, highly recommend it, absolutely. Wet sanding, using water with waterproof sandpaper, does several great things. It washes away the plastic debris so the sandpaper doesn't clog up as quickly.
Leaves things cool too, right? Reduces friction heat.
Exactly. It cools the surface, preventing accidental melting or deformation. And maybe most importantly, it drastically reduces the amount of fine plastic dust getting into the air, which is much safer.
Always wear protection though, especially if dry sanding. Mask, eye protection.
Non-negotiable safety gear.
Okay, so after sanding up to maybe P1200 or P2000 grit, what if the goal is that super smooth, almost mirror shine?
Then you move on to polishing. Once the surface is really smooth from the fine sanding, you can use a polishing paste specifically designed for plastics. Things like Brasso or Xeropol work well. Apply it with a soft microfiber cloth.
Can you use rotary tools like a Dremel with a polishing buff?
You can, but again, extreme caution with speed. Use the absolute lowest speed setting. generate too much friction heat, and you'll melt or distort the surface you just spent ages sanding smooth. Low and slow is key for polishing PETG.
Right. Patience again. Now, what about joining parts? If you've printed a large model in sections, here's where PETG's best feature, its chemical resistance, suddenly becomes a problem, right?
It becomes a huge obstacle for gluing. Unlike ABS or ASA, which you can easily solvent weld with acetone for a super strong bond, PETG resists common solvents. Acetone does basically nothing to it.
So acetone welding is out. What are our options for actually gluing PETG parts together effectively?
Two main reliable options. For smaller parts, or where you need a really fast, strong joint, cyanoacrylate glue, basically, standard superglue works very well.
Any tips for using superglue?
Using an accelerator spray can be really helpful. It instantly cures the glue, which is great for holding parts in place, and it can help fill tiny gaps. The main downside is that the superglue joint itself can be a little brittle.
But what's the stronger option, especially for larger parts or filling gaps?
For maximum structural strength, bonding larger surface areas, or where you need to fill gaps, a two-component epoxy is generally superior.
Takes longer to cure, though.
It does. But that longer working time can actually be an advantage, giving you more time to perfectly align the parts before it sets. And epoxy itself is very strong and adheres well to PETG.
Good to know. Okay, last finishing topic, painting. If we want to paint our beautifully sanded and maybe glued PETG model, what's the absolute must-do step for a good result?
Primer. Without a doubt, primer. After you've done all your fanding, filling any big gaps, maybe with a 2-part polyester filler, and thoroughly degrease the surface with something like isopropyl alcohol, applying a spray primer is non-negotiable.
Why is primer so critical on PETG?
Two main reasons. First, PETG can be a bit slick, and primer provides a uniform surface that the final paint layers can actually adhere to properly. Without it, your paint might peel or scratch off easily. Second, primer instantly highlights any tiny imperfections, small scratches, missed layer lines that you might have missed during sanding, giving you a last chance to fix them before the color goes on.
So primer first.
Yeah.
Then standard painting techniques.
Yep. Apply your chosen paint. Spray paints work well in thin layers, or acrylics for detail work. And finish it all off with a clear protective varnish, matte or glossy, to protect the paint job from scratches and UV light.
Okay, so sanding is doable, if laborious. Gluing needs epoxy, or CA glue. Painting needs primer. But what about the holy grail for smooth finishes, chemical smoothing? Is there any viable, safe shortcut for PETG like acetone provides for ABS?
This is really the main finishing disadvantage of PETG, especially if you're aiming for that perfectly smooth injection molded look purely for aesthetics. The short answer is basically no, not a safe or reliable one.
We know acetone doesn't work. Any other chemicals sometimes mentioned?
You might occasionally hear people mention solvents like ethyl acetate. Some report limited success, but honestly, the results seem very inconsistent. Often it just dulls the surface rather than truly smoothing it uniformly. It's not a reliable process like acetone smoothing for ABS.
Okay, but there are chemicals that can dissolve PETG, right? Just dangerous ones.
Yes, and we need to be extremely clear here. There are potent industrial chemicals, things like dichloromethane, often called DCM, or methyl ethyl ketone, MEK. These are highly toxic, volatile, and carcinogenic substances.
And they can technically smooth PETG.
They can dissolve it, yes. But let me say this unequivocally. These chemicals are incredibly dangerous. They pose serious health risks through inhalation and skin contact, and they require specialized handling and ventilation that make them completely unsuitable and unsafe for home or hobbyist use.
So the message is, don't even think about it.
Absolutely not. They are not a viable or safe option for anyone outside a controlled industrial environment with proper safety protocols. For PETG smoothing, you absolutely must stick to mechanical methods like sanding and polishing.
Okay, that's a crucial safety warning. So, wrapping this all up, what have we learned? Our deep dive really shows that mastering PETG means treating it less like a simple filament and maybe more like a bit of a chemistry experiment you need to control.
That's a good way to think about it.
Mandatory drying is step 0, right? Then that strict adhesion management, especially needing that separating layer on certain beds.
Crucial to prevent damage.
And then in the slicer, dialing in those very precise, often slower print speeds, but paired with those lightning-fast travel speeds, plus carefully managing the cooling fan. Those are the keys to getting a good functional part off the printer.
Exactly. What's really interesting is how PETG emerges as this functional champion, right? It wins on durability, toughness, chemical resistance.
Right.
It's great for mechanical parts, But that exact same chemical resistance, its star feature, means achieving a flawless aesthetic finish demands real physical labor. Sanding, filling, polishing, gluing carefully. There's just no easy, safe chemical shortcut like you have with some other materials. And that brings us to a final provocative thought for you, the listener. Given the PETG requires all this intensive mechanical smoothing work if you want it to look pristine, whereas materials like ABS or ASA can be chemically smooth quite easily with acetone vapor, how does this lack of a safe chemical shortcut for PETG influence your material choice?
It's a really important consideration.
Are you printing purely for function, where maybe the layer lines don't matter much and PTT's strength is paramount? Or is that finished, smooth aesthetic so vital for your project that you might actually need to reconsider ABS or ASA, even with their own challenges like needing good ventilation and managing warping?
Yeah, function versus finish and the work involved. It's a key decision point when choosing between these strong materials. Something to definitely mull over as you fine-tune those PTG slicer settings.